Ionic bonding at A level is actually simpler than it was at GCSE. This doesn't happen often, so let's take some cheer in that. We need to be able to draw dot-cross diagrams to represent the bonding in ionic compounds. So, for example, at GCSE, we might have drawn sodium, 2, and we go on 8. One, and then possibly shown that the sodium loses an electron to form a positively charged ion. We can assume at A level that it's only the outer shell electrons that we're interested in when we're bonding, so that is all we're going to show. This makes things much, much quicker. So I could now show it in the form of sodium with its outer shell electron. Chlorine. Chlorine has got 7 electrons in its outer shell. I'm going to use a different symbol. And we get the formation of sodium ions, positively charged, and chloride ions, which are negatively charged. So, a couple of key things here. Firstly, sodium, as is going to be the case with all our metals, has lost its outer shell electron. We do not draw the next shell in, we just show it as the symbol, no electrons and the positive charge. In this case, single positive charge, it's lost 1 electron. Chlorine, or the chloride ion, should I say, we are showing the outer shell of electrons plus the one it's gained, and again, keeping the symbols different so we can see that this electron did not originally belong to chlorine. We also need to be clear that when we move from atoms to ions, the size is going to change, or the radius, the ionic radius is going to differ from the atomic radius that we had before. So with cations, we would expect the radius, the ionic radius, is going to be smaller than it was as an atom. Why is that? Well, if we think about it, we've lost that outer shell electron, in this case the 3s1 electron. So we've got greater nuclear charge, it's pulling the remaining electrons in more tightly. We've got the opposite happening with chloride. With chloride, we've got anions are going to have a greater ionic radius in comparison to their atomic radius. For exactly the opposite reason, we have now got an extra electron but no more nuclear charge, no more protons, and the repulsion between the electrons is actually just going to push everything out just a little bit, so greater ionic radius. This is really important to note when we're looking at lattice diagrams for the structure, and often you are asked to label which is the sodium ion, which is the chloride ion, for example, and people often get it the wrong way round. Another term that you might hear at A level is that of isoelectronic, which simply means that 2 atoms or ions have got the same number of electrons. So let me give you an example. If we take the sodium ion, Na+, it had 11 electrons, it's now got 10. 1s2, 2s2, 2p6. It is isoelectronic with the noble gas that preceded it. Neon had 10 electrons, it's always got 10 electrons, 1s2, 2s2, 2p6. So we've got the same electronic structure for the sodium ion as the noble gas atomically, neon. They're said to be isoelectronic. With anions, then we have got a similar thing happening. Chloride ion, we've got 1s2, 2s2, 2p6, 3s2, 3p6 has gained an electron. Anions are going to be isoelectronic with the noble gas that comes after them in the periodic table. So for the chloride, that's going to be against argon, which has exactly the same electronic structure. The sodium ion and the chloride ion that I've just shown you are examples of simple ions, but we also need to be aware that we can have polyatomic or compound ions. Things that you might have seen before, the ammonium ion. So the ammonium ion. So we're talking about ions that have got more than one atom and element in them. Or perhaps the sulfate ion. Yeah, I still spell sulfate with a pH. That's never going to change. SO4 2 minus. Now, one of the things that you need to be very clear about is that the bonding within the ion itself is covalent. Let me show you this one because it's a very nice and simple example. So nitrogen, got its lone pair of electrons. It's got 5 electrons in its outer shell. It's bonded to 3 hydrogens, and it makes a dative covalent bond to a 4th hydrogen ion, and the positive charge is spread out essentially over the whole ion. So ammonium ions are capable of ionic bonding. So for example, we could have ammonium chloride, that would be an ionic compound, but the bonding within the ammonium ion is covalent. Ionic compounds are not molecular, so once we've formed, for example, sodium chloride, NaCl, it does not run around as little sodium chloride molecules or units. The sodium ions and the chloride ions, billions of them, come together to form a giant ionic lattice. And on the left here, I've got a picture of a sodium chloride lattice. We need to be very clear that the attraction between the sodium ions and the chloride ions, okay, let's go back to what I've just said. The sodium ions are going to be the smaller ones, and the chloride ions are going to be the bigger ones in this case. The attraction is between the sodium ion and all the surrounding chloride ions, between a chloride ion and all the surrounding sodium ions. It's essentially a non-directional electrostatic attraction. Non-directional electrostatic attraction. This is where I wish writing would just appear on my screen, but I'm not that technically able. The next one here is cesium chloride. As you can see, there's a slightly different arrangement of ions within the lattice. The sodium chloride lattice is said to have a coordination number of 6. Coordination number is 6, and that essentially means that each sodium ion is surrounded by 6 chloride ions and vice versa. For cesium chloride, the coordination number is 8, which you might be able to see if you can view this three-dimensionally in your head. Each cesium ion is surrounded by 8 chloride ions and vice versa. The arrangement that ions take up in a lattice is simply depending on the size and the charge of the ions, and it's just a play-off between the attractive and the repulsive forces. One of the properties of ionic compounds is that they are brittle, they shatter, and hopefully you'll be able to see that if you were to cleave the lattice at a certain point so that the chloride ions come into contact with more chloride ions, that repulsion is what would cause the crystal to shatter. We can get a feel for the strength of an ionic lattice by looking at the lattice enthalpy. It's given the symbol, capital Greek D, obviously, delta, which is drawn as a triangle, LE for lattice energy, H is for enthalpy, and under standard conditions. Don't worry about that if you haven't come across that yet. Essentially, the lattice enthalpy is just the amount of energy released when 1 mole of a lattice is formed from gaseous ions. We need to be really, really clear at A level that an ionic bond is not the formation of the ions themselves, it's the coming together of oppositely charged ions to form the ionic lattice. This is really just a measure of the electrostatic attraction, the amount of electrostatic attraction between oppositely charged ions. So, for example, if I were to take sodium chloride, I could write a definition for the lattice enthalpy for sodium chloride. So, sodium ions, chloride ions in the gaseous state coming together to form 1 mole, hence the way that the equation is balanced, of sodium chloride. And the lattice enthalpy for sodium chloride is minus 787 kilojoules per mole. So that is the amount of energy that's released on formation of this lattice. If I were to do the same thing for the cesium chloride lattice, we can see here to form cesium chloride, and the value for cesium chloride is minus 657 kilojoules per mole, i.e. a little less energy is released. And that would make sense because cesium ions are much, much bigger, and the single positive charge is spread out over a larger area. They're said to have a lower charge density, and they're just not going to be able to pack as closely together with the chloride ions, so not quite as strong an ionic bond. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free maths skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.